Yeah, hey everyone. Thank you so much for coming, and hope you all are doing well. So, today I'm going to talk about one of the key techniques of XAI, or explainable AI, and explore how we can move beyond just treating our ML models as black boxes. And I'm pretty sure chances are that you've probably been in that uncomfortable meeting where someone asks, but why did the model choose that, right? So I'm going to talk about that and also talk about some of the actionable takeaways that would help answer that question. So a little bit about me. So I'm based in the South Bay. I work as a staff data scientist at Intuit. For me, the best part about working at Intuit is that the work that I do matters. I get to work on models that help small businesses and also help people prosper financially. And that is why explainability is such a key and a strong pillar of the modeling process. So I work in the periphery of engineering and data science, so I like to get my hands full on both of those areas. So I like to be in the middle. That I love gaming, so I love PS5. I recently bought a Steam Deck. It's just amazing, the best thing ever. If you don't have it, please do. Then I love watching soccer and as well as tennis. I recently came here for the Laver Cup. It was awesome. Also, I like driving. I think driving is very therapeutic as long as a few things, or I would say a few conditions are being met. The most important one, that it has to be a stick shift. And this is me driving in Laguna Seca, like here near Monterey, and it was just a blast, the best day of my life, I would say. Okay, so now for today's agenda. So we'll just go over first, why does explainability matter to us, right, in this day and age? Then we'll talk about the theory and a little bit of the mathematical intuition behind that. Then we'll go over 2 case studies. I chose these 2 case studies because these are the most relevant ones in any industry. You have some decision tree like XGBoost or LightGBM, and also, of course, some deep neural networks as well. And finally, like every talk, we'll have some limitation slide as well. Okay, so let's talk about explainable AI, right? The problem is that we live in a world where ML is not just about fun projects anymore. It's much more beyond that. It's making decisions that affect people's lives, right? So let's say that when AI rejects a candidate's application, you actually deserve to know why, right? Is it their education, experience, or is it something else, right? So it's used in very crucial industries. Let's talk about the medical image diagnosis, right? So when an AI says that you might have cancer, well, both you and your doctor need to understand what the model saw in that image, right? And the same thing for getting a loan denied, let's say. Well, the algorithm said no, it's just not enough, right? You need to dig a bit deeper, what's really going on there, right? And of course, we also have some ethical concerns as well. So without explainability, we can't detect bias and ensure fairness or build trust there, okay? So before we move on to SHAP, we will talk a little bit about the Shapley values from where the whole theory is based upon, right? There are, by the way, many different techniques of XAI. This is just one of them, and this is one of the most widely tools that are being used, so I decided to cover this, right? So the formula looks something like this, right? So you got that? It's pretty easy, right? Right? Well, we can do better than that. So let's take a concrete example here, right? So let's imagine that 3 friends start a business, right? And they bring in some profit, let's say 20K, right? If Alice alone, by the way, those 3 friends are Alice, Bob, and Charlie, and if Alice alone worked, she would bring in about 5K in profit. If Bob worked alone, he would bring in about 3K, okay? And if Charlie, it would be 4K, right? But if you sum them up, that's actually about 12K, right? So the question here remains that, how can they fairly split the 20K profit, and also where did the remaining 8K come from? Well, that comes from the power of collaboration, okay? That is not really understood from looking just at the overall picture, right? So it could be that, if Alice probably brings in some X factor that the other two do not, right? Or what if, Bob and Charlie teamed up, what would happen then, right? So that's that's the whole thing, and that's the magic of collaboration, which is not really, understood fully, right? And that's the question that we're trying to answer, that how can we fairly split this profit, right? So let's look at the origins, right? So this originates from the game theory, okay? From just game theory, where the idea was to just reward, correctly or fairly the player who's playing the game, right? So, among different players, you would actually fairly distribute the rewards in like some sort of a cooperative game, right? But in terms of machine learning terms, we have a player could be a feature, okay? A game could be like any kind of an ML task, and an ML task could be a classification, regression, ranking, any kind of task really, right? And that's what we're going for, okay? Now we move on to SHAP, right? SHAP stands for Shapley Additive Explanations. It's been there, for a while now, right? And it's just a specific implementation of, Shapley values in terms of machine learning, okay? So the whole thing is just a linear model of feature contributions. We'll go into that. And the best part about it, though, is that it is model agnostic. Like in theory. In theory, it is model agnostic, meaning that the same, I would say, same foundations will actually work for all kinds of models. You name a decision tree, neural networks, any kind of, different clustering model you can think of. So, all will work, pretty good. And yeah, and let's talk about the mathematical foundation now. Okay, so we'll not go into too much detail technically here, but it's important to have a general idea of where all of this is coming from, okay? So we have this formula, right? SHAP tries to satisfy this equation right here, okay? So f of x is our prediction for a single customer, okay? Just one customer, all right? E of f is our baseline prediction, okay? So what would we predict if we knew nothing about a single customer, okay? And this is usually the mean prediction of the data set, like in real terms of the background data or something, all right? And then we have the phi, which actually tells us, how much does a specific feature push us away from the baseline, okay? And that is really the SHAP value for feature I for input x. That's what's going on, and that's what all of these algorithms are trying to satisfy, okay, in terms of SHAP. Now, how do we calculate SHAP, all right? Now, it's not that simple, because the SHAP calculation is actually exponential, all right? Meaning that its time complexity is 2 raised to the power m, right? So meaning that if, let's say, we have 3 features, and m is the number of features, by the way. So if we have 3 features, there would be 8 different combinations that you have to select and calculate on all of those things, okay? So it really bumps up and shoots up in the sky. Let's look at one question, okay? How much does each feature contribute to a loan application? Okay, a simple example. So, and we have 3 different features. We have age, income, and credit score, all right? Now, what we need to do in order to calculate SHAP is that we need to calculate all possible combinations of features, including where no feature is there, and including where every feature is there. So it would be something like this, right? So you have 8 different combinations. When you have no features, then you have each one of them, only them, right? And then you have a combination of 2, and you have the final all 3 of them. And you need to calculate how much each feature helps on average across all of these 8 different combinations. So that's the whole thing there, all right? Now, thankfully, people who are much smarter than me, they have this, approximation methods, all right? And these approximation methods are actually vary, but they are mostly of the 3 kinds. But there are actually, plenty more coming up as well, especially for LLMs and stuff. But in a broad category, we have the kernel SHAP, which is applicable to any kind of a model type, all right? But the problem is it's slow for large data sets. The tree SHAP, which is optimized for tree-based architectures. By tree-based, I mean everything, meaning decision trees, random forests, some boosted trees, gradient boosted trees, everything, right? Anything that has a tree-like structure. And it actually exploits that hierarchical structure to make some faster calculations. And then you have the deep SHAP, as the name suggests. It's for deep neural networks, and it leverages backpropagation to do this. All right? So let's see how all of these plays out, okay? So the first case study is about decision trees, right? We will be using XGBoost here, which is popular for so many different tasks, especially for tabular data. So we're going to focus on that. Now here, the business problem that I'm talking about, it's actually publicly available. So all of the code and all of the data is there publicly, so you can check. And here, really, the business problem is that there's a bank which tries to predict which customers will subscribe to a term deposit based on direct marketing campaigns, which is phone calls. And by term deposit, I mean some kind of certificate of deposit like CDs like we have, right? So that's the gist of it. So we have this data set. It's a tabular data. Features include customer demographics, some financial details about whether they own a home or something like that. And then they also have previous interaction history, whether the bank did try to contact them before and what was the outcome of that. So all of those things. It's a binary classification problem, so we have two things, meaning that yes, they did subscribe to the term deposit, and then no, right? So we have about 45K samples, and we are using the XGBoost classifier. Now this is the ROC curve for this, okay? And by the way, when I did this, I was not looking for the perfect model, right? So the whole concept is just to showcase XAI, but this is not bad. This is not too shabby, right? So we can trust our predictions and the explainability for this model here, right? So now, for the code part, there is the SHAP library that you can use, right? It's the way you do it is you just import it. And then what you do is that they have these explainer objects. So here in this case, we are dealing with decision trees, right? So what we are trying to do is we are trying to create this explainer object, okay, on the model, which is the XGB, that's the model, and then X test is actually the test data set, and that's how you create the SHAP values. Now these SHAP values are literally just a matrix, right? It's just a NumPy, so it's a NumPy array, right? So you have the length of the data, right? The number of rows and the number of features, right? But these values alone won't really give you anything, like any kind of intuition. You really need to plot them and see what is going on, right? So that's what we're going to do. So now the first plot is a global plot, okay? By global, I mean that you're looking at all of the data at the same time. You're not looking at one single prediction. You're actually looking at the full data. So this is the global plot, okay? And this is called a bee swarm plot because, I don't know, looks like a bee swarm, maybe. And a lot is going on here, all right? So on the x-axis, you have the SHAP values, right? It goes from 0 to negative and then positive, okay? On the y-axis, you have each feature. And then on this data, you have some kind of a color coding there, right? So you have a feature value. It goes from low to high, all right? So now, let's look at what is really going on there, right? So this is basically a high-level model summary of the model's behavior, okay? And each dot here is actually just a data point, okay? And it's useful for understanding the overall impact for each feature, okay? Obviously, the features are actually ordered by their importance, meaning their Shapley values or SHAP values. And the way it looks at where we need to look at is that widespread means that the feature impacts different customers differently, okay? And the tight clusters mean they are actually more consistent, okay? Now the main thing to know here is that, the main thing here is that it's not the absolute values that matter, okay? It's the relative values, right? So in this data set, for this model, you have these kind of values, but in a different data set or even with a different model, you will have a different kind of Shapley values, right? But the main thing is that it's the relative values between those features that matter there, okay? So as I said, it actually represents the impact of each feature has on the model's prediction. Now we get into the root cause of it, right? So the positive SHAP values indicate that the feature pushes the model prediction higher, that is towards the yes class, okay? So the positive values is the yes class or the 1 class, which in our case is basically saying that the person did subscribe to the term deposit, all right? And the distance from the center indicates the magnitude, okay? Now, an interesting thing is that the categorical variables are actually displayed in gray, okay? Why is that? Because you can't really have any kind of ordering there. Okay, we don't know what order they are in. So we have to look at a different kind of graph to really know what's going on there, all right? Now, even here, we can do some sample insight generation, right? So let's look at, let's say the fourth feature, which is the balance, right? So it really means that the customers with more balance in their accounts are more likely to subscribe to a term deposit. Why is that? Because you see the red values are actually on the positive end of the SHAP values. Okay? So higher values, meaning the customers with more balance in their accounts are more likely to subscribe, right? And let's also look at one more thing, maybe. Let's look at the campaign feature there, okay? So this really means, the name is a little bit misleading, but it really means that the customers who have been contacted more frequently in the current campaign are less likely to subscribe, right? So which means that if there is somebody, or the bank has been targeting one customer more and more, okay? So you see the red values on the left. It basically means that more time, the more you reach out to them, the less likely they are to subscribe to us, right? So that's how it is. And this is pretty interesting. And you can generate some cool insights out of these. And you can really know what's going on in the business, really. Okay? So remember we talked about the categorical variables which were grayed out. It was not possible to look at them. Now, these are the dependency plots. And dependency plots really come in handy when you are zooming in into one single feature, okay, and how it behaves like for the whole data set, right? So in this case, and this is much easier to read, by the way, and in this case, it's the same thing. It's just you can think of it, it's kind of flipped because the SHAP values are on the y-axis, right? And the actual categorical values are on the x-axis for this, right? So let's look at the top left, right? So the top left is basically saying that homeowners are less likely to subscribe, right? So you can see that housing, in the housing one, if they have a home, most of the SHAP values are actually lower, right? So that is pretty interesting. The second one, if you look at the bottom left, right? It basically means that single and divorced customers are more likely to subscribe there within this data set, and that's what the model thinks. Okay. Now, if the previous marketing campaign, if you look at the bottom right, if the previous marketing campaign was successful, then the chances increase dramatically. You can see that if it was a success, it is not even there, not even one dot is there below that dotted line, right? Which means that it's a very good indicator. Now, not all features are actually good separators. You can look at the education, which is the top right. So it's not a good feature that actually separates out things, right? So that's good to know there, right? So in this manner, we can make some informed decisions about the business right there, and that's the whole point, all right? So now we come to the second case study, which is about deep neural networks, and I really wanted to picture or maybe choose some kind of a data set which is completely different to the first one. So this, in fact, it is a completely different problem. It goes from binary to a multi-class classification. It goes from a tabular to a time series. Of course, a complete model change and also a different data set, all right? So here, we're looking at CNN, okay, or convolutional neural networks, and we're also looking at the human activity recognition data set, okay? So picture this. We have 30 volunteers between ages 19 and 48 who wore smartphones on their waist and went about their daily activities, okay? The phone's accelerometer and the gyroscope captured every movement that they made, right? And that's how it is. And the goal here is to classify those signals into 6 different activities. Those are walking, walking upstairs, walking downstairs, sitting, standing, or lying down, right? And if you think about this problem is not just academic, right? I mean, this technology powers all kinds of fitness trackers, right? Like your watch or Ring, right? And so any kind of a fall detection systems, and that people use all the time. So if our CNN can actually distinguish between walking upstairs versus downstairs using only sensor data, what exactly did we learn? I think that's the crucial question that we are trying to ask here, right? So, all right. So let's look at the problem, right? So we have this data set. It's a multivariate time series, we know. We have 560 features, These are all numeric, so no categorical features right here. We have these accelerometer readings on the XYZ axis and the gyroscope readings, which give us things like the angular velocity, the angular acceleration, and all of that, right? And these features are already engineered, so I'm not doing any kind of feature engineering there, right? There are 6 classes, as I said, and this is a multi-class classification. So the model that I used was a 1D CNN using PyTorch. That's how I trained it. And the only pre-processing that I did, which is necessary for any kind of neural network, is just normalize the data between 0 to 1. Although that in itself is not necessary because this data in itself is normalized. But anyway, I did it anyway. So, and then the next thing is, of course, this is a time series, so you have to convert it into a window sequences, right? So you have to have a sequenced data for it to really consume the right way, right? So this is how I did the classifier. This is a very simple thing. I mean, it's a 2-layer CNN with just a tanh activation. Is nothing fancy. Again, the goal was on explainability, not on the model performance. But with that said, it really did quite a decent job. So if you look at the F1 score, it's pretty good. It's actually able to just separate out these 6 classes pretty well there. Okay. So now for the SHAP calculation. Now here is something that we really need to do first thing, right? We need to create a background data set. Remember that mathematical formula that I said, right? That we have a background data set, the expectation, that is what is really important here. We need to have a balanced background data set. Now there are many different techniques you could do that. You could actually just sample out just a random sample to make sure that you are getting the same distribution as your test data or training data. Here in this case, I just made sure that I have 120 examples, okay, 20 per class. So there has to be 20 for each class just to make sure that I have all classes there. And that's it. You don't need to create more than, I would say, 200 examples there in the background data set, okay? Now here you can see that I'm using the deep explainer, which is the deep SHAP, right? And the SHAP values that you get is actually in a 4D. Why? Because you have many different things around here, right? So you have the first thing that you have is the number of rows, which is 1,000 in this case because I just sliced it. Then you have 561 features, okay? You have 64 is our time dimension, which is the number of time steps there, okay? And 6 is the number of classes. Now remember, in order to visualize, we have to convert this into 4D to 2D, right? And the first thing we need to do, we need to normalize along the time step, which in this case, I just took the last time step, but there are different ways. You can just take the mean or whatever, right? Or the median. But in this case, I just took the last one. And then you're going to select a class that you are interested in plotting. So in this case, I took the walking class, which is the 0th index, okay? So by the way, this is much more computationally intensive than pre-SHAP, but it reveals the complex temporal patterns, right, that we need. Okay, so the concept is still the same. It's a global explanation. It's a B-swarm plot, right? These are the features here, right? But the main thing to note here is that this is a multi-class setting. So we have a set of SHAP values for every class in a 1 versus all. So in this case, for example, we are looking at the walking class. So SHAP values which are positive, it means that the model is thinking about the walking being positive and negative for all other classes. Okay, so it's 1 versus all, right, in this case. Again, the positive SHAP values pushes the feature towards the positive class, which is walking in this case, and the negative ones push towards all other classes here. Okay? So now let's see what the model thinks about walking versus everything else, right? So let's look at the first feature, right? It's the angle between the gyroscopic mean and the gravitational mean. So it basically says that when walking, the angle between the mean gyroscope signal and the mean gravity signal is smaller, okay? And in the fourth feature, you could see that there is some kind of an acceleration in the x-axis. And low values of gravitational acceleration on the x-axis, it pushes the prediction away from the walking class because you could see a lot of blue there, all right? So, but what's amazing is that our CNN discovered some human biomechanics here, right? It learned that walking creates a specific signature in how our body moves in relation to gravity, okay? Now let's look at something else, okay? And this is where things get interesting because sitting and lying are both stationary activities, okay? No walking, no climbing stairs. But it's very interesting if you look at the top 3 features. They're exactly the same, but both activities rely heavily on gravity acceleration along the x-axis. But notice the pattern there, it's actually completely flipped. Okay, so the pattern is completely opposite while sitting and lying down, and that's what the model is actually deciphering from all of this data, and this is what it's learning along the way, right? So I thought that was pretty cool. And then, here in this case, the dependency plot, by the way, I mean, last time in the decision tree, we had some categorical variables, so dependency plots were more useful there, but nevertheless, you can have this, you can see this, and you can get a better idea of how the clustering is kind of done in terms of the data points. So here, if you look at the top feature, again, this is between walking upstairs and standing, you can see that the pattern is still flipped, is actually flipped, right? So this is again, the angle between the mean gyroscopic mean and the gravitational mean, it's kind of flipped again, right? So lower value of the feature is indicative of walking upstairs, while higher values actually pushes the prediction towards standing there, right? Now, the next one is, now, all of these times, right, we have talked about the global explanations, meaning that we are looking at the full data set and all of its features. We went to the dependency plots, which actually focused or zoomed into one particular feature, right? But it was still along the full data set. Now, this is where SHAP is pretty interesting, because you can not only do the global, but also the local explanations pretty well, right? By local explanations, I mean that you are actually zooming in into one single individual, okay? Like, just one single person, okay, in this case. In this case, you're looking at one single person, right? So, like here you can see that this is actually a bar plot, okay? And, but the concept still remain the same. In the x-axis, we have our SHAP values, and in the y-axis, we have all of these features which are most important for this particular instance or individual. That is not for the whole data set. So the red values basically mean that this is why the model is thinking that this person should be lying down, okay? And the blue values, the small blue values, are some of the negatives that it sees that, okay, maybe this person is not lying down, right? But most of the time, you can see that it is positive, especially on the top ones, which are the gravitation or the gravity-related features. They're actually all red, right? So you can see that it's mostly red, right? And it's the same thing, right? The positive SHAP values push the prediction towards the lying class, and the negative ones push the prediction away from the lying class here, okay? So, of course, there are some limitations, and these are something I think one should be really mindful when looking at these predictions and going to the stakeholders regarding them, right? The first thing is that SHAP explains the model, not the reality. So this is not really how the world works, but it's just how the model thinks the world would work, okay? So if your model is poorly learned, this might be completely wrong, right? Because your model might be, which is very important, which is why it's really important to really see the accuracy of the model, okay? Accuracy or your evaluation metric, just to make sure that the model is learning the right thing and is able to do the right predictions, okay? In most of the time. But yeah, I mean, that is something that really need to be taken care of, right? That's not the truth. For large data set, it's really computationally intensive, especially when it comes to deep learning models. And the bottlenecks really come with the background data set, the size of the background data set, the model complexity, number of layers you have, like, things like that. The number of features, of course, that plays a big, I think I would say the biggest role. And also if it's multi-class versus, is it a binary classification problem, right? So the next one is, of course, well, not of course. This is not very something you would notice right away. But when you start doing this, you realize that for the features which are highly correlated, right, SHAP values can be misleading. And why is it misleading? So let's say that we have two highly correlated features, age and years of experience, okay? So what would happen is that SHAP would arbitrarily split the credit among them, okay? So every time you run it, it will actually split it in a different way. So that's something you need to be wary of. So I personally, what I do, I make sure that I remove some very highly correlated correlated features, just using a correlation matrix and just to be on the safe side. And then, I think this is something which is very crucial, which is these are not causal effects. This is still an ML model, so it shows you the feature contributions, not the causal effects. And of course, the results depend very widely on the choice of the background data set, especially for the deep learning models, where background data set is very much essential for that, right? So with that, thank you so much. This is the QR code for the GitHub with all the code and the slides. We have the notebooks right here. Connect me on LinkedIn, and we have a talent and a page, add into it. I would love to talk about it as well. So yeah, thank you so much.